Okay, so we're going to start talking about motion and changes in motion. So when we think about changes in motion, that's the acceleration that we were finding in the previous unit. What we were finding there is how the acceleration occurs. This unit is going to be more about what does the acceleration do to an object? What does it look like when an object's accelerating? Can we find an object's position or distance traveled or whatever based on knowing that acceleration and some other initial conditions? The study of motion, of moving objects, is called kinematics. So this chapter is a chapter on kinematics, and the next one is as well. We deal with kinematics in one dimension. In other words, you can either go side to side, that's it, that's one dimension, or say up and down, that's another dimension. Just whatever we do in this chapter, we will limit ourselves to situations where objects only go in one of two directions, which means that's one dimension. So we do one-dimensional kinematics here, and we'll do two-dimensional kinematics, objects moving through two dimensions, in the next chapter. So if we're only dealing in one dimension, position. Position is just where you are at any given point. It's a given location. It's a location somewhere. Now to establish that, the simplest way is to just draw a number line. 1, 2, 3, 4, 5, 6. We call some point in the room or whatever on this line 0, and then let's say we call this point here 3 meters from that. This location right here, this is a position. So if I had an object that was here, we would say its position, we're left and right, so we'll go x, is 3 meters. So if I asked you, how far did it go to get to that point? Well, the answer to that question is, I don't know. It depends on where it started. And we might assume that it started, here at 0, but it may not have. What if it started at this location and went from here? So we'll call this its initial position. Let me double check your formula sheet. So I'm looking at your formula sheet now, and they were going to use x sub 0. So we'll do that. So your original, try to be consistent with the formula sheet. So your original position might be here, and your position later on, I'll put a little f here for final. Sometimes we don't write any letter there for the final, but that's all right. To illustrate it, we'll do that. So let's say I started here at, let's see, that would be 1, 2, 3, 4, at negative 4 meters. Well, that means my displacement is an arrow going from where I started straight to where I ended. It is a vector. So your position, to recap, is where you are in any given point. Your displacement is if you go from one locate position to another, you have created a displacement vector. And it is a vector quantity. In this case, in fact, your displacement would be simply your change in position, change in, and anytime you have a change in, it's going to come up a lot in this unit, anytime you have a change in something, it's always the final minus the initial. So your final position minus your initial. So your final position was 3 meters minus your initial, which was a negative 4 meters. Of course, 3 minus a negative 4 is just 3 plus 4. So I have a positive 7 meters as my displacement vector for the magnitude of my displacement. But you know what? The direction is also built into this because, and we're generally going to assume this all along, left to right, if you're going in that, something is displaced or moving in that direction, we'll call that positive. If something is displaced or moving in this direction, we'll call that negative. So generally, left is negative, right is positive. It doesn't have to be that way, but if we assume it that way, agree to do it that way, it'll be some consistent descriptions when we talk about things. So in this case, I kind of am given it by saying positive 7 meters, that is a displacement. This is my direction, and the 7 is my magnitude. So keep in mind, you don't even have to end up, say, in the positives to have a positive displacement. For example, what if, similar situation, draw a number line, boom. let's say here's 0. And let's say I go from -9 as my original position, and my final position was -2. So x final is -2. What's my displacement? Well, I went from here to there, and I went, in quick inspection, I went up 7, didn't I? So let's go through and see it. My displacement, magnitude of my displacement, actually the displacement is going to be, because I'm building the positive negatives into the situation, -2 meters is my final, minus a -9 meters, which is going to be equal to -2 plus 9, which is positive 7 meters. Notice I have the same displacement I had before. This direction, 7 meters. But notice I didn't have to end in a positive. It's the direction, my displacement still came out positive. So position is where you are. Does not necessarily have to be how far you went to get there. Now I will point this out real quickly. If, and we will do this as often as we can, if we assume that you start at 0 and you displace, say, positive 7, then yes, your final position is the same as your displacement. And many times it just makes more sense to say, well, we can start anywhere we want, let's make it 0. But not every problem is that an option. So we should understand the subtle difference between displacement and position. All right. Now we're going to get a little more subtle, or a little, maybe not more subtle, but a little nitpicky with words. In physics, there is a difference between distance and displacement. Displacement, like we just looked at, is a vector quantity. It has a magnitude, how far you've gone, and a direction. Also, it only cares about where you start and where you end. In other words, it only cares about your original position and your final. That's it. It doesn't care really what you did in between. So, distance, on the other hand, is a scalar quantity and doesn't involve direction, so just magnitude. And it is the total path, not just, it considers the total path, not just your starting and ending. So an interesting situation arises. If I were to go from here, my house, we'll draw a house, there we go, boom, and go walk my dog in this crazy path and end up at a friend's house, my displacement would only be concerned with from here to there. That would be my displacement. Just the vector pointing from where I started, right, to where I ended. Now, it's hard. This is obviously not a one-dimensional situation because I moved both left and right and up and down, but to illustrate the point. Distance, on the other hand, would be this entire path that you walked. Sorry, I can't see that. There we go. It'd be that entire path. So it is possible, for example, to have a displacement of 0 and yet have a distance of many miles. If I had left my house, done this, but at the end just came back to my house, my displacement would be 0. I didn't change my start and end are the same. You subtract them, you get nothing. But my distance would be something more than that. So it is a subtle difference. Oftentimes, for one-dimensional motion, distance and displacement are the same. But for example, what if an object starts at this location, goes here, then goes back again, and then comes over here and stops? Its distance would be different than its displacement. Displacement would just be that. The distance would be the total back and forth that it did, of that total sum of what it walked or ran or drove. Remember, displacement is a vector quantity. So continuing with this theme, speed and velocity, one is a vector, one is a scalar. Your average, both are, we're going to deal with the averages first. So when you think average speed or average velocity, you want to consider a beginning situation and the ending, you may not be concerned, in many cases, with what happens in between. Speed, well, it will use the total path. For example, average speed is going to be the distance you travel, not the displacement. It's a scalar quantity. Speed is a scalar quantity over the time it took. Whereas average velocity is going to be your displacement vector divided by the time it took. Velocity is a vector. So in the previous example, this would be that whole path that you walked your dog. This would only be from your house to your friend's house. So your average speed might be larger than it would be larger than your average velocity. Physics, we don't always, average is great. And by the way, you're calculating your average velocity, for example, is simply going to be your final position minus your original position divided by the time it took you to get from one to the other. So notice it is exactly what it says it is. It is displacement divided by the time it took. But what if that, in fact, you can do this. What if this change in time, what if I don't want to shrink that down to a second and then a half a second? And then what happens as the time I consider it gets smaller and smaller? Well, I go less of a distance, but this ratio might not change. And what we're finding in that case is, on the next slide, is if we take, and this is for you folks that are taking calculus, as delta time, we'll clear that out. I'm going to do this right. Boom. So we're actually taking the limit as the change in time goes to zero. As you approach a no change in time, what would happen to this? Well, what you get when you do that is something called the instantaneous, there we go, velocity. And give you an example of this. When you're driving along in your car and you glance at your speedometer and it says 50 miles an hour, that's how fast you're going at that instant. However, if you're on a long trip and you make a few stops, your average speed, your total displacement for the trip, divided by that time, the total time, is going to be something less than 50. That would be your average velocity. So your instantaneous is literally at some infinitesimally small point in time, how fast are you going? So velocity is a vector. It has magnitude and it has direction. So what are the ways we can change a velocity vector? Well, think about it. What's the way you change your velocity? The simplest way I think most of you would go right away is you could speed up. So one way to change velocity is to go ahead and increase the magnitude. Speed up. Increase magnitude. Another way to change velocity would be to hit the brakes and slow down. And that, of course, would be to decrease magnitude. But what if we don't mess with the magnitude at all? It's a vector. There's another thing we can mess with. What if we turn or change direction? That's no change in magnitude, right? You just change direction. So there's three possible ways to change your velocity. In your car, there are three things that you can change velocity with. You could hit the gas pedal, you could hit the brake, or you could turn the steering wheel. In a physics classroom, every single one of those would produce a vector called acceleration. So an acceleration is any, in a physics class, any change in velocity. Does not just mean speeding up like it would out in the real world. If you say accelerate, people always think speed up. That's fine. That's out in the real world. In a physics classroom, technically speaking, somebody turns, you can say, ooh, you're accelerating. And they are, even though they're not speeding up or slowing down. If you see somebody run across the road, if you're driving with a physics person, you can say, hey, accelerate. And they'll know to hit the brakes, because that's another form of acceleration, is to slow down. Acceleration, lowercase a as we know, in the units of meters per second, change in speed per second. There's 2 seconds. If you want to think of it this way, when you accelerate your car, you might pick up 8 miles an hour, looking at your speedometer, right? 8 miles an hour, you may pick up that much speed every second. Notice roughly the units are the same. Distance divided by time divided by another time. So we don't use miles per hour in physics, we use meters per second. But it's a change in speed, so I might pick up 8 miles per hour every second. Notice this time shows up twice. So let's look at how each of these happen. So, acceleration is a vector quantity. That means, as you know, it has direction. If you've been half asleep watching this video, you need to pay attention now, my friend, because this is really important. Just because acceleration is a vector and has a direction that it's pointed does not necessarily mean that is the direction that you're moving. Is not necessarily. The direction that you're moving. What vector is the direction you're moving every time? That would be velocity, right? Your velocity vector is the direction you're moving. So here's what I want to point out. So if I have a ramp, I don't want that ramp. Do I? No, I want one that stretches out. Hold on. This ramp. That'll work. All right. So if I have a ramp and I have a cart or a ball or something on that ramp, in fact, I don't even need to put the cart or the ball on it yet. Which way does this ramp that I've drawn, which way does it accelerate things? Which way do you think its acceleration is always pointed? You look at it and you're like, well, acceleration is always going to be that way. You would be right. But notice, I don't need an object on the ramp to know that. This ramp, one of the properties of the ramp is that acceleration. But doesn't mean an object's going to necessarily be going in that direction. You give enough time, it might. But for example, let's do the simplest case. If I put a ball or something on that ramp and I let it go, what will it do? Before you even took physics, you would say it would speed up, right? Going down the ramp, it would speed up. It would move this way, which would be its velocity vector. Notice its acceleration vector would be pointed right along with it. That's because if an acceleration vector and a velocity vector are pointed in the same direction, I don't care what direction that is, but if they're pointed in the same direction, you will speed up. That's the definition of speeding up. Your acceleration vector is with your velocity vector. So in this case, they're both pointed the same way. But you're like, well, Born, I thought you said that they wouldn't necessarily point the same way. You're absolutely right. Because what if I start by rolling this ball up the hill, up the incline? So I push it initially and I let go, and it's got a velocity, and it's moving up the ramp. Now, notice I haven't changed my acceleration vector, because that's a property of the ramp in this case. Now you tell me, if you roll a ball up a ramp while it's headed up the ramp, what does it do? Speed up, slow down? I think we would all agree that it would slow down. What do you notice about your acceleration vector and your velocity vector? You got it. They're opposite directions. So if your acceleration vector is one way, but your velocity is the other, then you are slowing down. So we still describe the change in velocity as acceleration, but its direction as a vector is pointed against velocity. So you could say it is decelerating, slowing down. Now we're going to forget the ramp entirely and talk about the one case where you change the velocity but you don't change the magnitude. Let's say that you are moving, looking at it from above, you're in your car, you're going this direction. If your acceleration vector is pointed exactly perpendicular to your velocity, you will not speed up or slow down. This acceleration vector is not with you or against you. It's like neutral. What it will cause you to do is turn. So this is how you turn. It happens when your acceleration is perpendicular to your velocity. In fact, when those two vectors are perpendicular. So the only time your acceleration vector points with your velocity is when you're speeding up. If you're slowing down and turning, it doesn't point at all like your velocity. So when I throw an object up on the way up, which direction is its acceleration? If you said up, you're not thinking, slow down. If you throw an object up, as soon as it leaves your hand, which way is acceleration because of gravity always pointed? It's down. Every single time, right? If you throw an object up in the air, all right, I'll go, I need space here. So if I throw an object, as soon as I let go of an object, so I take a ball and I throw it through the air, heck, that's two-dimensional motion. But it doesn't matter. As soon as it leaves my hand, acceleration is downward. In fact, we know that acceleration to be the acceleration due to gravity. Right? No matter where I am, I don't care what it's doing, going up or going down, its acceleration is directed downward. Velocity would actually be like this, like that, and like this in that case, tangent to the path. But I'm not really worried about that. The point is that you don't know for sure. So if I throw an object straight up, its velocity might be up, but its acceleration, as long as we're on Earth, is down. And it's that value. All right, calculating acceleration, well, here's the deal with acceleration. Acceleration is your change in velocity, but it's not just your change in velocity because, for example, my Hyundai can get to 80 miles an hour, eventually. And when they advertise sports cars, they say 0 to 60, and then they don't stop there. There's more to that statement, because if it was just 0 to 60, most cars can do this. But they 0 to 60 in whatever seconds. Notice, it's your change in velocity. Not only that, not only you can go fast, get to a different speed or speed up or slow down, depends on how fast you do that change. So acceleration is a change in velocity over the change in the time it takes. Change in final velocity minus your original velocity divided by, we just use time for change in time. So pointing out the acceleration is v final minus v original over t. That also means, by the way, you can solve, for example, let's solve that for v final. So we'll multiply both sides by t. I got at equals v final minus v initial. And then I'm going to write that the other way around. So v final minus v initial equals at. Just one's on the left now, one's on the right. And I'm going to add the VO to both sides. So your final velocity would be your acceleration times your time plus however fast you were when you started. Now, the only thing I will point out is that you'll see going forward, if you glance at your formula sheet, they don't usually use V final. So V equals AT plus VO. The absence of any letter here indicates it's your final or velocity at some later time. It is the velocity that corresponds to whatever time you plug in there. And this is the first of a set of very important equations called the kinematic equations. And that number one, we'll get to the rest during next class. Have a good night. I'll see you tomorrow.